I'm Güvenç, and today I will explain my code and I will run these code files on my terminal. And first let's start with MPI program. So in this program I use only MPI for distributed computing, and the basic logic works as follows. When the program starts, I initialize the MPI environment and learn each process identity rank, and I also find out how many processes are running in total. I get the metric size from the command line, then I try to divide the rows equally among the processes. But if they don't divide evenly, I give the remaining rows to the first process. And in the memory management part, I allocate space only for the rows each process will handle, like local A and local C. But for the B matrix, every process needs to complete matrix, because in the matrix multiplication, each row of A is multiplied with all columns of B. So the master process creates all matrices and fills them with the random numbers. And also there is a critical point here. Before broadcasting the B matrix, I copied the full B array, and because the MPI bcast function sends data from the full B address, and if I don't do this, copy operation full B remains empty and all calculations same out wrong. So in my previous tests I made a mistake initially and the results came out as 0. So I fixed that issue, and I sent the B matrix to all processes at once with MPI bcast. This is collective communication, meaning all processes participate in this operation, and I use MPI security. So, and after this, to distribute the A matrix, because each process can receive a different number of rows, so I keep track of how many elements each process will receive in the send counts array and where they'll start in the display array. After each process receives its own rows, it works independently. I perform standard matrix multiplication with 3 nested loops. So the other loop for my own rows, the middle loop for the result matrix columns, the inner loop iterates for the multiplication operation, and then I collect the results rows calculated by each process at the master process with MPI gather V, and the complete result matrix is formed. For verification, I sum all elements. This is why I can check whether calculation makes sense, and I use the C++ chrono library for time measurement and get results with microseconds. And now let me get into MPI and Open MP program. So in this program I use MPI and Open MP together to provide parallelism both between process and within processes. The basic idea is I distribute work to different machines with MPI, and I use multiple CPU cores on each machine with OpenMP. I use MPI init treat and instead of normal MPI init, because treat support is needed, and I request the MPI treat funneled level so that only main treat makes MPI calls, and I get both metric size and treat count from the command line. I determine how many trees I will use with OMP set num treats. So after this, work distribution and broadcast operations are exactly the same as pure MPI. I divide rows among process, copy and broadcast B, scatter A. The real difference appears in the matrix multiplication loop. I wrote pragma OMP parallel for schedule, and right above the other loop. This is an OpenMP directive and tells the compiler parallelize this loop, and the reason I use dynamic scheduling is so threads get new rows when they finish their work. So if some rows are calculated faster, the workload is balanced, and the OpenMP runtime automatically distributes loop iterations to threads, and each thread processes one or more rows, manage private and shared variables. And for example, if I give an example, like if I have like two MPI process and two threads running in each, I have a total of 4 parallel processing units, two processes distributed across Docker containers, two threads in each process using CPU cores. This two-level parallelism is very suitable for modern cluster architectures because it uses both like inter-node network communication and inter-node multi-core process together. So that's why I used, and the inner two loops run independently by each thread, so there is no race condition because each thread writes two different rows. And thanks to the OpenMP compiler directives, I achieve significant performance improvement with very little code change. So I did MPI gather verification and time measurement work the same way as pure MPI. And if I explain my MPI in OpenCL program, in this program I tried to use OpenCL for GPU acceleration, but since there is no GPU in the Docker environment, it fell back to CPU. So for that reason, that code use CPU, and OpenCL is designed for heterogeneous computing, and meaning we can run the same code on different type of processes. So first I defined the kernel code as a C string, and after that this OpenCL C language and the kernel void matrix mult function is written in the OpenCL C language and will run in parallel on the GPU. Each work item finds its own position with the get global ID function and calculates one matrix element. And I use the float data type because GPUs are generally faster with single precision floating point. The MPI part is the same again. Row distribution to processes, broadcast, scatter. OpenCL setup is quite complex. First I found the OpenCL platform with the CL get platform IDs. Then I look for GPU with CL get device IDs. If I can't find one, I fall back to CPU. So I create context to manage OpenCPL objects and memory. I create command Q. Like so I can Q and the execute commands. I compile the kernel program at runtime. This way the code is platform independent, but compilation can fail, so I check for errors, and if it fails I use CPU fallback. If compilation succeeds, I create the kernel object, allocate buffers for buff A and buff B. I use CL mem copy post host PTR to copy from host memory to device memory, and for buff C I only allocate write only space. I set kernel arguments in order with CL set kernel arg, and I set global size 0. After that I run the kernel on a 2D grid with CL NQ ND range kernel, and I set I set global size 0 local rows and global size 1 n, which means local rows and work items run in parallel and each calculates one element. I copy the result from device memory to host memory, which with CL NQ read buffer. So I can so after that I clean up all open CL objects with CL release functions with like buffers, kernel, program, queue, context, and that's how is my code works.